Okay, good afternoon, everyone. So this is the week 5 tutorial interpolation. So how do we find the Lagrange form and the Newton form of the polynomial of, in this case, we have 4 points of degree 3. Yeah, because you have 4 points, so you have degree 3 polynomials that interpolates this data set. Okay. So we will do it on a piece of paper. So now let me share my piece of paper. Stop this one and I share my document camera. Okay, so now you have, so question number 1. Okay, so you have x is 0, 1, 2, 3, and y is -4, 3, 2, 5. So what is the Lagrange form? So the Lagrange form, first we have to construct the Lagrange polynomial. So L1 will be x minus everything except the first point. So this one is the first point, yeah? So this one, 1, 2, 3, 4. So x minus everything except the first point. X minus 1 first, yeah? Then x minus 2, and x minus 3. See, so except the first point. So, and then the first point minus everything else. So first point is 0, minus 2, minus 3. Okay. And you can simplify this. So this one is 1, 2, 3, so minus 1/6. Yeah, so x minus 1, x minus 2, x minus 3. Okay. And you do the same to get L2. So L2x will be x minus everything except the second point. So x minus 0, what is just x? Then x minus 2, x minus 3. Okay, and the second point is 1 minus 0, 1 minus 2, 1 minus 3. Yeah, and you simplify this, you got, so 1 here, it's 1 minus 1, and this one is minus 2, so you got 1/2. Okay, then x minus 2, x minus 3. Yeah, so this is your L2, and then your L3 is x minus everything except the third point. So x minus 0, x minus 1, x minus 3. Yeah, you skip the third point, yeah? And then the third point is 2 minus 0, 2 minus 1, 2 minus 3. Okay, and you simplify it. So this one is 2, this one is 1, and this one is minus 1. So minus 1/2. And x minus 1, x minus 3. Okay, and the last one is just the same, yeah? So x minus 0, x minus 1, x minus 2. You skip the last one, yeah? So then you have the last one is 3 minus 0, 3 minus 1, 3 minus 2. And then this one gives you, so 3 here, 2 here is 6, it's 1. So 1/6, x minus 1, x minus 2. Okay. And what is the polynomial? So the polynomial P. P just, so P of x, yeah. It's just the data value, minus 4 L1x plus 3 L2x plus 2 L3x, okay, plus 5 L4x. So you can expand it out or you can leave it like this, okay? But if you expand it out, then it will be something like this. So minus 4. So you can leave it like this, okay? You can stop here. But if you're curious, you can expand it out and it becomes minus 4 plus 15x. So you can expand it by hand or by maple. Yeah, so it will be a cubic polynomial of this form. Okay. So that is a Lagrange form. So any question? So far so good, right? So this is a Lagrange form of the interpolation. And now how about the Newton form? So now let me work on the Newton form. So the Newton form, then first you have to construct a divided difference table. Okay, so the divided difference table is, you have x here, you have y here. So x is 0, 1, 2, 3, and y is minus 4, 3, 2, 5. Okay, and now you construct the divided difference over 2 points. So this one will be 3 minus 4, yeah, divided by 1 minus 0. So we're just 7. Okay, and you do the same here. So 2 minus 3, okay, divided by 2 minus 1. So give you minus 1. Yeah. And then this one will be 5 minus 2 over 3 minus 2. What is just 3 over 1, just 3. Okay. And then how do you find this coefficient? Well, you just take 7 minus, well, maybe we just take the minus 1 minus 7, yeah. So maybe minus 1, okay, so minus 7, yeah. Take this one, minus 7, over, so now we have to be careful, okay? So we have to go down here, go down here, go down here, and take this point, okay? So 2 minus, and now we have to go up this range, and stop here. So 0. Okay, so you got minus 8 over 2 is minus 4. Okay, and similarly here you have 3 minus 1 over, so here you have to go down to 3, yeah. And then here you have to go up here to 1. Okay. So then you got 4 over 2, just 2. Yeah. And now for the last one. So now for the last one, then so for the last one, you just take 2 minus 4 over. So now we have to go down this way. Yes, I give you 3. And up here, go down to 0. So 0, yeah. So then we got 6 divided by 3, just give you 2. Okay, so I can, yeah. So now we have to extract the coefficient. So remember, the divided coefficient will be this one, yeah, this one, this one, and this one. Okay, so what is the Newton form? So now P, okay, so P will be -4, yeah, so -4 come from here, plus 7. Okay, so 7 is the divided difference over 2 points. So now you have to take x minus 0, yeah, and then, well, x minus 0, just x here, and then -4. Okay, so now I have to take x minus 0, then x minus 1. Okay, and now the last one is just plus 2, x minus 0, x minus 1, x minus 2. And then we stop. So we don't go to the next term, okay? So we never use the last term. So we have the cubic and we stop here. And if you're curious, yeah, you can expand it. Okay, you can expand it out. And if you expand it out, it will be -4 plus 15x minus 10x squared plus 2x cubed. So it's identical to Lagrange form. Yeah, so it has to be identical to the Lagrange form because over four points, there's a unique cubic polynomial that goes through that 4 points. Okay. So you can see it. The first is -4, right? Yeah. And for the x, you have 7x come from here. Yeah. And 4 plus 4x come from here. So 7 plus 4 is 11 already. And then here you have x and 2x and 4, right? So and 4x. So the 4x plus 11 become 15x and so on. Yeah. So any question for this? So that is question number 1. And if you so go back to the problems. So now you see that the second problem is identical. Okay, so we don't spend time doing the second problem because it's just the same process but different data points. Yeah, so -2, -1, and 0 and 2 for the x, and for the y vectors you have 1, 4, 2, and 4. Okay, so you can work on this one. Okay, so how about number 3? So number 3 is about the errors between the approximation, the interpolation polynomials, and the exact function. Yeah. So now we do number 3. Yeah. So number 3. So now we do number 3. So number 3 is about the errors between the interpolation and the function. And if you remember, the errors is defined to be f of x minus Pn of x. Yeah. And we proved in the lectures that the error function can be given by the derivative of order n plus 1 at some point xi over n plus 1 factorial, okay, times the product of x minus x1, x minus x2 up to x minus x n plus 1. Okay, so that's what we prove in the lectures. And now this one is just a an application, a simple application. So what is the degree now? So degree is n equal 2, right? Because quadratic, yeah. So now we just have n equal 2. So when n equal 2, you have e2 x equal f of x minus p2 of x. Okay, and by the theorem, it's just some derivative of order 3 at some point. Okay, because remember n plus 1 here just equal 3 over 3 factorials. Yeah, times x minus x1, x minus x2, x minus x3. Yeah. So remember we have 3 points. Yeah. And so what are those 3 points? So remember so now we have two pieces of assumption. So first we have 3 point is x1 equal 0, x2 equal 1, and x3 equal 2, right? And the second piece of information is f triple prime is less than or equal 3 for all x in 0 to 2, right? For x in 0 to 2. So now I can put this one in. Yeah, I want to put this information in. So I said that, okay, so this one less than or equal. So now because this one less than or equal 3, you take the absolute value. Yeah, so now I take e2x absolute value, and then this one less than or equal 3, and 3 factorial just equals 6. Yeah, and I take absolute value, so x minus x1 is 0, x minus x2 is 1, and x minus x3 is x minus 2. Yeah. Okay. And then what is the point x? So the point x is just 1.5. Okay. So now what is the error at 1.5? So now if you plug it in, so e2 at 1.5. Okay. We just equal. So now if you plug it in, remember, so we have 1/2 here, and 1.5 minus 0, 1.5 minus 1, 1.5 minus 2. So this one is, sorry, 3/6 is 1/2, not 1/6. Yeah. So 1/2, and this one 1.5. So this one is 0.5. Yeah. And this one is minus 0.5. Take absolute value is 0.5. Okay. So then now you have numbers. So you just plug it in the calculator or MATLAB or whatever. So you got 0.1875. Okay, so that is the errors function. Okay. So any question about this one? Any question? So far, so good. Yeah. So no question. Yeah. Okay. So now the next one will be. So the next one will be. Okay. So we can write the Lagrange polynomials in this form. Okay. Sum of f of xi li. Yeah. So we can understand this like a map. We can understand like, you take a function f and you map it in a polynomial Pn equal Lf. Yeah. And Lf can be given by this formula. Okay. So the Li are just the Lagrange interpolation polynomials. Show that L is linear. So if you remember the linear maps in linear algebra, okay, the linear maps condition say that if you take L, you apply to a linear combination of two function f and g. Okay, any linear combination, yeah. So a and b are real numbers. Then it has to be, you know, the plus here, yeah, can be print outside, yeah. So it become a plus like this. So ALF plus BLG. So how do we prove this? So so we prove this by just the definition, yeah. So now if I try to prove this, so then so remember my LF, okay, it just equals sum of f x I L I, right? I run from 1 to n plus 1. So now what is L? But instead of f, I put in AF plus BG. So A is some real number, B is some real numbers, F and G are just functions. Yeah. So how do I write this? So how do I write this? Well, you see that I just replaced F by, you see here F here, then FXI, right? So now I just replace F by AF plus BG in this sum. Yeah. So I just replace this by AF plus BG in this sum, right? SXI, LI. I run from 1 to n plus 1. Yeah. So you see, you just replace F here and F here. So here AF plus BG, so AF plus BG. That's it. And now, because you see, I mean, this one is just, you just have a sum of two functions. Yeah, you apply to a point. So you can write down actually just a sum of AFI plus BGXI. Right? So you can write down like this. Sum of LI. I from 1 to n. Okay. And now I multiplied it out, right? So I just multiplied out. So the sum is still the same, yeah. But now maybe some n plus 1, yeah. But now I multiply Li inside. So if I multiply Li inside, I have AF XI Li plus BG XI Li. Yeah, so I just multiply Li inside, right? But now, you see, I sum over these terms, yeah? And because the sum is linear, so I can split it into two sums. Split it into separate sums, yeah? Sum of BGXI Li. Okay, so I split it into some like this. Okay, and now you realize that A is a constant. It doesn't depend on the sum. So you can take it out. And B is the constant. You can take it outside. Okay, so now you can take A outside and you got sum of FXI Li. I from 1 to n plus 1. Yeah. Sorry. And here you have B sum of GXI Li. I from 1 to n plus 1. Yeah. But what is this one? What is this term? What is this one? So Anyone? So what is this? What is this term? Yeah, somebody say something. L of F, yes, correct, yes. So this one just L of F multiplied by A. Yeah, and this one is just be L of G. And that's it. So you prove it. So you prove. You see, we start with LAF plus BG, right? And then we split it into ALF plus BLG. So it's a linear map. Okay. Yeah. Okay. So now the next one. So the next one is so now go to the next one. Yeah. So the next question is very interesting. So the next question is number 5. And actually this one is an exam question last year or 2 years ago, I forgot. But you see now the sum of Li, the sum of all the Lagrange interpolation polynomials equal 1 for all x, not only for 1 point, but for all x. Okay. So now how do we prove it? So first, before we prove it, let's check whether it's correct or not. Okay. So now suppose I want to check it first. Yeah. So suppose I want to check this condition. Yeah. I want to check whether the problem or the theorem is correct or not. So now I want to check. So suppose I have only 2 points. Yeah. So n equal 2, or maybe 2 is a bit too complicated. Maybe just take n equal 1. Okay. So n equal 1 means that you have only 2 points. So x1 and x2. Okay. Then what is the Lagrangian L1? So what is Lagrangian L1? What is L1? So remember the formula. So x minus everything except the first point, right? So can anyone write down what is the Lagrange L1? What is L1? So L1 is just x minus the first point, right? Over x, the first point, x1 minus the second point. So this is my Lagrangian, yeah, the first one. Okay. So just a linear function, yeah. And so what is L2? What is L2? So I wrote down L1 already. What is L2? Anyone remember the formula? Now see, you look at L1. Yeah. You see that x minus, well, actually, sorry, the first one is not correct. Yeah, x minus everything except the first one. So it should be x minus x2. Yeah. And then the first point minus the second point. Yeah. Now what is L2? What is L2? Anyone? So you see L1, if you put in L1 x1, yeah, it will be x1 minus x2 over x1 minus x2 and it equal 1. Yeah. So the Lagrangian formula and L1 x2 it just equals 0 because you plug in x2 here, x2 minus x2 equals 0. So this is the property of L1. Yeah. Okay. Yeah. So somebody said that. Okay. So x minus x1 over x2 minus x1. Yes, correct. Yeah. So x minus everything except the second point. Yeah. Over the second point minus x1. Yeah. So that's correct. So now you take L1 plus L2. Okay. And you will have x2, maybe x1 minus x2, right? Of x minus x2, right? Yeah, but because you see the second one, if you multiply by minus 1, yeah, then you got x1 minus x2, right? So then this one just minus x plus x1. Okay. And so now x got cancelled. Yeah. And then you got x1 minus x2 over x1 minus x2. So it's equal 1. It's just equal 1 for all x. So this one is for all x. Yeah. Okay. So you can do the same. You can do the same for n equal 2. And you get the same results. Yeah. But for n equal 2, it takes a bit longer calculation because now you have more terms, but it will be correct. Yeah. So now how do we prove it? So now how do we prove it? So now how do we prove sum of Lix equal 1 for all x? Okay, so maybe the hint is like this. Okay, now if you remember, we take L of f, right? L of f is Pn, yeah? It's just sum of f xi, Li. Right? So what special function f, to make this and this are the same? So how do we choose f to make this formula and this formula are the same? So what special function f we should choose? So anyone? So how do you choose f? Okay, choose a special function f. Yes, just choose f equal 1. Okay. So if you choose f equal 1, okay, so now if I choose, so I want this, yeah, so this is what I want, yeah. So now if I choose f to be 1 for all x, yeah, for all x, then I have L of 1. Okay, it just equal Pn equals sum of 1 Lix. Yeah. Well, but then can we conclude that L of 1 equal 1? So is it over? Is it done yet or not? So can we say that this one equal 1 for all x? Can you say that I'm done here? I mean, L1 just equal 1. Well, so remember, you see this one, if you remember this formula, right? So this one just implies that f of xi equal Pn at xi, right? Because Pn is the interpolation polynomial. So it is identical at the interpolation point. Yeah. So here, you know, when you choose f equal 1, yeah, then you just have the interpolation condition. So you know that Pn will equal 1 at xi, I from 1 to n plus 1. Okay, you just have the interpolation condition, yeah. So essentially you just have a function Pn, and it equal 1 here, yeah, at x1, x2, up to xn plus 1, right? But how do we show that, you know, in the middle, it has to be equal 1 as well? How do we show that it's equal 1 in the, you see the point, right? So the point is we just know that, okay, if you choose f equal 1, then you just have Pn equal 1 at those interpolation points, yeah? But you are very close, yeah? So now what we need to do is we need to prove that, you know, actually in between, it has to be equal 1 as well. Okay, I mean, it cannot go up or go down in the middle. So how do we do that? Well, maybe it's not easy to see in the general case, but now suppose I take n equal 2, right? So now if I take n equal 2, n equal 2, right? So take n equal 2. So how many points do we have here? So we have 3 points. Yeah? You have x1, x2, and x3. Okay. So now you choose your f to be 1. Yeah. Okay. So your Pn will be sum of Li x will be L1 plus L2x plus L3x. Yeah. But actually n equal 2, so I should write 2 here. I run from 1 to 3. Okay. Then I know that P2 at x1 has to be equal 1, has to be equal P at x2, has to be equal P2 at x3. Yeah. So I have, okay, now I have 3 points. Yeah. So this one, my x1, x2, x3. And I know this one, it has to go to 3 points here. So everything is 1. Okay. But then how do I know for sure that P2 has to be equal 1 everywhere? So can it go up and down in the middle? So can it goes up and down in the middle? So anyone? So how do we show that P2? So what is a P2? What is P2 here? What is the degree of P2? So what is the degree of P2? Anyone? P2 cannot be, I mean, the degree cannot be 3. Remember Pn. No, cannot be 1. Pn is degree n. No, because remember we have n plus 1 points. Okay. And then we interpolate by Pn. And Pn is a degree n. And here n equal 2. So what is the degree of P2? 2. Yes. Okay. So P2 has to be a degree of P2. Remember, Pn is a degree n. Yeah. So if you write down L1, yeah, if you write down L1, then you have L1 is just x minus everything except the first point. Right? So you see that L1 has degree 2. Yeah, yes, you are close. Yeah. So now we need to, okay, so now we need to show that, okay, so it's a parabola, right? So you know it's a parabola and it go through 3 points. Yeah. And now we have to say that why this one, you know, is a straight line. We know it, but you see that there is a, at least you see that there's a relation between the degree of polynomials and, you know, the number of points. Yeah. So you see it's a parabola, right? So parabola, and it goes through 3 points. It goes through 3 points at 1. Yeah. And we want to show that it has to be identically 1 everywhere. Okay. So how do we show that? So we have to use some theorem. I mean, you have to justify this by some theorem. Okay. So what is the correct theorem to say here? Well, what is the correct theorem? So now, I mean, if I define P, well, so suppose I define, say, P2 minus F, okay, what is just 1? Okay, I define this one to be G, yeah? So Gx, yeah? Then what do I have? Then I have G of x1 equals 0 equal G of x2 equal G of x3, yeah? Okay? Because the interpolation condition, right? And now, so now I have, what is the degree of G? So degree of G is 2, right? Because Pn degree 2 and this one degree 0, so degree of G is 2. So now G equals 0 at 3 points and degree is 2. So can we say that G equals 0 everywhere? Can we say that G has to be equal 0, identically 0? So what theorem? So a parabola, I mean, G is a parabola, right? So because it's parabola minus 1, yeah? And parabola equal 0 at 3 points. Then how do we say that equal? It has to be equal 0 and everywhere. So what is the theorem? Anyone remember the theorem? Okay, so if you remember the fundamental theorem of algebra, okay, so fundamental theorem of algebra, say that because G has at least 2 0, right? So you have and degree 2, right? So degree of G equal 2, right? Then G can be factored into a form like this. So x minus the first roots and x minus the second roots. Okay, so this is a fundamental theorem of algebra because degree 2, so you can have only 2 roots. Yeah. So remember this theorem. And now, you see, now if you put in x3, okay, so now remember we have x1, x2, x3, all of them equal 0. Yeah. So now if you put in you put in x3, and then you have a x3 minus x1, x3 minus x2, and those terms are not 0, right? Because the points are different, yeah. But you know that this one equals 0. So what is the conclusion? Conclusion is a has to be equal 0. Okay, the coefficient has to be equal 0. But if the coefficient equals 0, it means that g equals 0 everywhere for all x. Okay, so the whole point of this one is the consequence of the fundamental theorem of algebra. And it ties up with the degree of a polynomial. Okay, so you have more than 1 0 than the degrees. Yeah. And that's why, you know, I mean, go through 3 points. And if it equals 0 at 3 points, then it has to be a 0 polynomial. Okay. So you get the idea, right? So you have 2 steps. You cannot say that, okay, take f equal 1, then I can prove the sum of Li equal 1. It's not done yet. I mean, you have to invoke the fundamental theorem of algebra to say that, okay, because it equals 1 at n plus 1 points, and the degree is only n. Yeah, so you see, you can you can make this proof for the general n, right? For general n, then instead of having only, okay, so maybe let me write down the general case. Yeah? So the first step is we choose f equal 1. Then you have sum of Lix equal, so you have Pn, yeah, Pn n plus 1, yeah, and you have Pn xj equal 1 at xj j from 1 to n plus 1, yeah, and then you define q to be Pn minus 1. Then degree of q is n. So by fundamental theorem of algebra, so fundamental theorem of algebra, yeah. Then q has to be equal a x minus x1, x minus x2 up to x minus xn, right? And you put in qxn plus 1. Okay, then you have a xn plus 1 minus x1 dot xn plus 1 minus xn equals 0, right? So remember, before we have to say that this means that q x1 equals 0 up to q xn plus 1, yeah. Okay, so we have to use this condition. And then this implies that a equals 0. Okay, it's implied that q equals 0 everywhere. And hence Pn equal 1 for all x. Okay, so therefore sum of Li x equal 1 for all x. Okay, so that is the proof why y the sum of li has to be equal 1 for all x. Okay. Yeah. So any question? And then the last question is just a consequence of this question. So if you if you take the last question, the last question is just proving this sum. So question 6 is proving this f minus pn is the sum of fx minus fxi li. Okay, so we just have f of x equal f of x multiplied by 1, right? And remember, we just proved that the sum of li equal 1. Okay. And now you have Pn. Remember, Pn is a degree n, yeah? The sum of fxi li. So this one you can write down, you know, you take fx inside the sum. Now you take the difference, yeah? You take the difference between the first and the second equation. So f x minus pnx is just f of x minus I li. That's it. So so just a consequence of the previous question. Yeah. So nothing new here. Okay, so you just replace 1 by sum of li. Yeah.